Let's look at the reaction of nitrogen and hydrogen gases when they form ammonia. The reaction is reversible, so we use this double-sided arrow for its equation. While the forward reaction produces ammonia, the reverse reaction decomposes ammonia back into nitrogen and hydrogen. Which of the two reactions do you think happens faster? And how can we find out about the concentrations of the substances in a reaction once it reaches equilibrium? This information can be found through the equilibrium constant of a reaction. In this video, we will learn what the law of mass action is and how it is used to derive the formula for the rates of forward and reverse reactions. We will also learn about the equilibrium constant and its units. Let's take a closer look at the reaction to produce ammonia. 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. Suppose that we have 5 moles of nitrogen and 15 moles of hydrogen to start the reaction. Let's draw a graph to keep track of the number of moles of all substances in the reaction as it proceeds. Initially, even though many moles of both gases are present, only 1 mole of nitrogen will react with 3 moles of hydrogen to form 2 moles of ammonia. This is called the active mass of a substance. Active mass is the amount of substance that is actually reacting to form a product in a reaction at a certain time. As the reaction proceeds, the second mole of nitrogen will react with 3 more moles of hydrogen to form 2 more moles of ammonia. If the forward reaction keeps proceeding, we will see that eventually all the moles of nitrogen and hydrogen will be used up to form 10 moles of ammonia. But notice that this reaction is reversible and occurs in a closed container. At some point, the molecules of ammonia will begin decomposing into molecules of nitrogen and hydrogen, and the rate of reverse reaction will also begin to rise. But how do we calculate these rates? After studying reversible reactions, 2 Norwegian chemists, Goldberg and Waj, proposed the law of mass action. It states that number 1, the rate at which a substance reacts is directly proportional to its active mass. Number 2, the rate of reaction is directly proportional to the product of the individual active masses of the reactants. Let's look again at the reaction of ammonia production. It will take more time for 1 mole of nitrogen and 3 moles of hydrogen to react than 2 and 6 moles of nitrogen and hydrogen respectively. As the number of hydrogen and nitrogen molecules increase, the likelihood of successful collisions between them to form ammonia also increases. Therefore, the rate at which a substance reacts is directly proportional to its active mass. But how do we calculate this rate? A reaction happens only when a successful collision between reactants leads to a product. The number of successful collisions will depend on many factors. For example, the shape and orientation of hydrogen and nitrogen molecules, their kinetic energy, the temperature, and so on. We will group these factors into a constant number which we call the forward reaction constant, Kf. In order to find the rate of forward reaction, Rf, the reaction constant will be multiplied by the likelihood of successful collisions between hydrogen and nitrogen to form ammonia. Since there's only 1 mole of nitrogen, the likelihood of its successful collision is the same as its concentration, which is the number of nitrogen molecules in a given volume. However, as there are 3 moles of hydrogen, the likelihood of successful collisions for the first, second, and the third mole of hydrogen will be calculated by multiplying the concentration of hydrogen 3 times. In other words, the concentration of molecules is raised to the power of the number of moles for each reactant when it is multiplied with the reaction constant Kf. This is how the rate of reaction is calculated. Similarly, the rate of reverse reaction, RR, is equal to its reaction constant, Kr, times the concentration of the products raised to the power of the number of their moles. At equilibrium, the rates of forward and reverse reactions become equal. After rearranging the equation, we can give another name to the constants, Kf divided by Kr. We will call this new number the equilibrium constant, Kc. Equilibrium constant is defined as the ratio of the concentration of the products to the ratio of the concentration of the reactants in a reversible reaction when it reaches equilibrium. So far, we have only looked at the reaction of ammonia production. For any reaction, the equilibrium constant can be calculated using the general formula shown here. The units of equilibrium constant depend on the reaction. For example, let's look at these two reactions. Since mole per decimeter cube is the unit for concentration, we will substitute it in the formula. Pause the video here and try to solve it on your own before continuing. As you can see, these two reactions have different units for their equilibrium constants because of the different number of reactants and products and their molar ratio. So, in this video, we learned that the law of mass action is used to derive the formulas to calculate the rate of forward and reverse reactions. The equilibrium constant has this expression or formula. The unit of an equilibrium constant depends on the moles of the reactants and the products by using these examples.